discuss this theorem. So in this theorem, we have a matrix space XD and G is subset of X. We have to prove that these two statements are equivalent. So let us do that. I'm going to consider the A and we will prove B. Consider G is an open set. Getting? And what we have to prove? To prove that G does not contain any limit point of x minus g. We have to prove that G does not contain any limit point of x minus g. So let us take one limit point of x minus g and we will prove that it is not in G. Let small x be a limit point of x minus g. So you are familiar with the definition of limit point. So definition of limit point says, so therefore what can we write? For any r greater than 0, bxr minus singleton x intersection x minus g is not equal to phi. This is statement number star we have. Okay, by definition of limit point we could write it. But see, what is our target? Our target is to prove that G does not contain that point. To prove that limit point is not a member of G. See, normally when we have to prove something, we assume contrary. So here also I will do the same. Let it possible x belongs to G. So let it possible x belongs to G. But a very important thing we have, that is assume G is open set. Okay, but G is open. So you know the definition of open set, x belongs to G, G is open. So there will be an open ball around x which entirely lies inside G. So therefore there exists R1 greater than 0 such that Bx_R1 subset of G. That ball with center x and radius R1 entirely lies inside G. If you remove center of that ball from a ball, then also it is a subset of G. If you remove its center, getting, then also it is subset of G. See, it is subset of G. That means intersection of that ball with x minus g is phi. I will show you here. A small diagram I will draw here. Suppose this is matrix space and this is set G, getting, and there is one ball Bxr with center x and radius r. So if that ball lies inside G, then intersection of that ball with its complement is phi. So therefore Bxr1 minus singleton x intersection x minus g is equal to phi. Getting? Which is contradiction to equation, that statement number star. In star we say such intersection is non-empty, but there we are getting intersection is empty. So we get contradiction. We get contradiction to star. So that means our assumption is wrong. What was our assumption? Let it possible x belongs to G is wrong, therefore x does not belongs to G. I am going to write that thing. Before that you can make a screenshot of it. So therefore x does not belongs to G. So therefore we conclude that G does not contain any limit point of x minus G. So therefore G does not contain any limit point of x minus G. Of x minus G. See, conversely, we are going to assume part B and we will prove part A. Conversely, assume that G does not contain any limit point of x minus g. And what we have to prove? We have to prove part A, that is we have to prove G is open. This thing we have to prove. What is the technique to prove any particular set is open? We take one point, arbitrary point, and we try to find a ball around that point which entirely lies inside a given set. Then we can declare it is an open set. So the same technique I am going to use. I am going to take one arbitrary point from this set G. Let x belongs to G. But see, G does not contain any limit point of x minus G, and x belongs to G. That means 101% x is not a limit point of x minus G. You are getting? So therefore, x is not a limit point of x minus G. We could write it because of our assumption, by our assumption. Okay, because of this assumption we get x is not a limit point of x minus g. So you are familiar with the definition of limit point for every r greater than 0, bxr minus singleton x intersection a, whatever the set, not equal to phi. But it is not a limit point here. That means exactly opposite definition we supposed to write there. So let us write. So therefore there exists some r greater than 0 such that bxr minus singleton x intersection x minus g is equal to phi. In definition of limit point we write it is not equal to phi, but this is not a limit point, so that's why I supposed to write is equal to phi. Getting? So see what I want to say in diagram I will show you. Suppose this is a matrix space X and there is ball. Getting? So see, suppose this is G, ball with minus singleton X. Okay, its intersection with complement of G is phi. That means definitely that ball lies inside G. Getting? Since its intersection with complement is non-empty. Sorry, is empty. So therefore, what can we say? Bxr minus singleton x subset of G. Basically, x is in G and this ball also is in G. So that's why there is no need to subtract. So because of that one, I can write bxr subset of G. I will mention the reason because x belongs to G. So that's why it is possible. So see, you remember we started with what? We started with a single point from G, arbitrary point, and we could find open ball around that point which is a subset of G. So therefore definition of open set is satisfied here. Therefore we can declare G is an open set. Make a screenshot of it, then we will go further. So therefore finally we can declare G is an open set. So we started with by assuming a statement B and we proved A. So in both ways we have done. So therefore we can say statement A and B, both of them are equivalent. Okay, so in this way we have completed the proof of this theorem. Make a screenshot of it, then we will stop. Thank you. Bye bye.